Everybody around them is also.
Okay. Let's get back to business. Our next speaker is Thomas Barrett, who has come all the way down from Santa Barbara to tell us about coordinates and space-time structure.
Thanks. It's always good to be here. So, my plan for the next 15 minutes or so is to just soberly reflect upon what just transpired. So, in particular, I didn't actually know that there were going to be two screens. If I knew there would be two screens, I would have picked maybe one screen too many. I'm going to unravel some simple corollaries that follow from the stuff that JP was just talking about. Okay, so I'd like to begin by telling a parable. Consider two-dimensional Euclidean space. So we're all familiar with this mathematical object. It is well known that there is more than one way to present the structure of this object. Two in particular will be of interest to us today. Okay, so first, one can present the structure of Euclidean space by in the standard differential geometric manner. First, define the smooth manifold R2. You lay down the standard Euclidean metric on it. Just a particular smooth tensor field on R2. Okay, so we are all familiar with this way of presenting Euclidean space, and in the circles in which we all travel, this is the standard. There's another way that you can do it. So in the second method, one begins with set R2, but instead of defining smooth manifold structure on this set and then laying down a tensor, one instead singles out a collection of privileged coordinates on the set. So let me give some examples. So for example, the standard XY coordinates, we'll consider those privileged coordinates. We'll consider rotations of the standard XY coordinates. Those will be in our collection of privileged coordinates. Translations of standard XY coordinates, we'll consider those in our set of privileged coordinates. Reflections, we'll consider those in our set. And that's all. Those are all the privileged coordinates that we're throwing into our set. We're not throwing in stretches of the standard XY coordinate system, not in our set of privileged coordinates. Or bends of the standard coordinate, the XY coordinates, that's not going to be considered privileged. Okay, so I've told you exactly what the privileged coordinates are on R2. So in essence, what one is doing in this second presentation of Euclidean space is the following. We're saying that the structure of our space is given by those features that are shared in common or agreed upon by all of the privileged coordinates in our collection of privileged coordinates. Another related way to think about this is what we're doing is we're singling out a collection of symmetries of our space, the changes between one of our privileged coordinate systems with another one of our privileged coordinate systems. And we're saying that the structure of the space is given by those features that are invariant under these changes. Okay, so I will come back to a related point in a bit to make this idea precise, but it just so happens that the coordinatizations that I just singled out on the previous slides as privileged, what they agree upon is just the smooth manifold structure of R2 and the Euclidean metric and metrics isometric to it. Okay, so we have a second method of presenting the very same structure that we presented using the standard differential geometric framework, singling out a collection of privileged coordinates. Okay, so this is this parable. So the moral of this parable is sometimes put as follows. So this is Jill North in her recent book on this and related stuff. So she says the following. She says, as we see in the case of the Euclidean plane, the kinds of coordinates we can use for a space can indicate its structure. there are two ways of characterizing a given structure and two ways to learning about it, two routes to learning about it. A structure can be characterized more directly, as in the case of the Euclidean plane and the metric tensor, or it can be characterized less directly by means of the coordinate systems, the privileged coordinates for the space, and the features that are invariant under transformations of them. This sentence right here is the one that we are going to be asking about today. We're going to be asking whether there are always these two routes available, whether you can always do this second route in particular. Okay, but first, a bit of bookkeeping. So there are various names that folks give to this second method. David Wallace, John Norton, a lot of other people call the first method Riemannian, some places, the second method Kleinian. John Norton occasionally calls the first method additive, the second method subtractive, and Neil has called the first method, Neil Tier has called the first method internal, the second method external. And these are like all good names. I like all of these names. They're all good for different reasons. Our aim today is to investigate the second method, this Kleinian subtractive external method. And we're just like going to see how far we can push this thing. We're going to see like how far we can successfully go, like how much of general relativity in particular can we present using this second method. So our question is this: can all relativistic spacetimes be presented using the second Kleinian subtractive external method? Which ones can, which ones can't? Okay. So who cares? I care. And I actually don't even think I need to tell you why I care. But I put slides in telling you why some other people care. I care because this is just an interesting question in its own right. Other people care because it ties in with various things that folks have said about coordinates and structure. Okay, so let me give you some examples. Actually, another answer to you all care. So these slides are somewhat unnecessary, but I put them in here so I have to click through them, and so I'll say stuff. Okay, so many philosophers and physicists have suggested that we can use the privileged coordinates of a theory as a window into its structure. Okay. So North, for example, writes the following. I could quote other people, but I've read her book recently. So she says, there's an important difference between those features of a space that are agreed upon by all of the coordinate systems we can use to describe it, privileged coordinates, and the features that vary with choice of coordinate system. The former get at the true nature, the genuine structure of the space. The latter don't. Okay, so the idea here is that if you know the privileged coordinates of a space, you know what its structure is. The privileged coordinates determine its structure, because the structure of an order is just the stuff that's agreed upon by the privileged coordinates. And this idea is echoed in the common refrain that we should pay attention to coordinate systems in which a theory's laws take a nice form. So this is something that folks often say. Here's North saying something that's closely related to it. Okay, so we're going to investigate our question today by employing a particularly nice, clear framework that was recently introduced into philosophy of physics by David Wallace in his paper, Who's Afraid of Coordinate Systems? So this is the framework of locally G-structured spaces. Okay. So in brief, a locally G-structured space is just a set with a collection of maps from that set to Rn. Well, think of the maps in this set C as the privileged coordinates. Like, all we're doing here is singling out a collection of privileged coordinates. And so David remarks that this framework provides a legitimate and informative way to formulate theories. And he provides evidence for this claim by working through a number of helpful illustrative examples how to use locally G-structured spaces to present various different geometric objects that one might encounter in physics. Okay, so all we're doing today is we're examining where the limits of this framework lie, like how far you can push this method of presenting a geometric space and still have it work. Okay, and in doing so, we're asking the extent to which privileged coordinates determine structure. Okay. we first need some preliminaries. And in order to even define a locally G-structured space, I have to take one small step back and define another thing first. So we'll start there. One has to start somewhere. We're going to be starting with the pseudogroup. Okay, so if you have a topological space, a pseudogroup on a topological space is just a class of homeomorphisms between open subsets of this space, and this class satisfies some group-like properties. Okay, so in particular, like properties like, for every open set, the identity homeomorphism from that open set to itself, that's in your pseudogroup. If some homeomorphism is in your pseudogroup, its inverse, also homeomorphism is in the pseudogroup. If you have two maps in the pseudogroup that are composable, then their composition is in stuff like that. The composition is in the pseudogroup. Group-like properties, the stuff that you would expect. Okay, examples. One particularly simple example that will be important in what follows. If you have a smooth manifold M, the class of diffeomorphisms between open subsets of M, that's a pseudogroup. Okay, this is going to be the biggest pseudogroup that we're going to be considering. Another important example, if MG is a relativistic spacetime, then the class of diffeomorphisms between open subsets of your manifold M that preserve the metric G, that's a pseudogroup. And we'll call it the isometry pseudogroup of the spacetime MG. So we can think of the isometry pseudogroup, just unraveling an intuition here, we can think of the isometry pseudogroup as kind of like, it's playing the same role as the isometry group of the spacetime, just when you're allowing in local symmetries, like symmetries that hold between small regions of your spacetime, in addition to the big stuff, the global symmetries, okay? Important note, we'll come back to this in a bit, Heraclitus spacetime in JB's terms is one with a trivial isometry pseudogroup. So, or in other words, its pseudogroup only contains identity maps. This is slightly different from the definition that JB gave. It is equivalent to the definition that JB gave. I mean, in essence, what we're saying here is a Heraclitus spacetime has a isometry pseudogroup that is as small as one can get. It only contains identity maps, okay? Minimum collection of symmetries. Okay, so now we have the resources necessary to define a locally G-structured space. Okay, so let G be a pseudogroup on Rn that's contained in the pseudogroup of local diffeomorphisms of Rn. So this is the pseudogroup I defined a couple slides ago. Another way to say this, let G be a pseudogroup on Rn such that all of the maps in G are diffeomorphisms between open subsets of Rn, okay? Now, a locally G-structured space is a pair SC, where S is a set, and C is a non-empty collection of injective partial functions. So their domain might not be the entirety of S. Injective partial functions from S to Rn, and a few natural properties are satisfied by this pair. So in particular, every element of S is in the domain of some or other element of C, so like your privileged coordinates cover S. The ranges of the maps in C are open subsets of Rn, and most importantly, the collection C plays nicely with your pseudogroup G, in the sense that the maps in C are required to satisfy a compatibility condition that's analogous to the kind of compatibility condition that one requires of holding between n charts on a manifold. Okay, so we can think of the elements of C as the privileged local coordinates on our space X. That's the important thing. Here's a picture. So we have our pseudogroup G defined on Rn. We have our set S, and we have our collection of privileged coordinates from S to Rn. And the maps in C play nicely with the maps in G. Okay, so I'm going to ask a collection of questions today, 4 of them to be exact. We'll go through them. The main question is question 2, but we need to do a little bit of work before we get there. So the first question is this: how do we recover a manifold with structure on it from a locally G-structured space? So we have this like privileged coordinates presentation. How do we recover back a manifold with structure from that? Okay, so this is the first kind of question that I'm gonna answer. Okay, so 2 steps. First, we need to recover smooth manifold structure on S, and then we're going to have to recover some tensor fields on top of that smooth manifold structure. Okay, so first step first. We recover smooth manifold structure on S in a totally natural way. This is super intuitive, the way that one does this. It's easy. We just consider each function in C as an n-chart on S in its own right. So we're thinking of this now as a coordinate chart on S. Consider all coordinate charts of this form for the maps in C. Now throw in wholesale all of the other coordinate charts that you could put on S that are compatible with all of the coordinate charts that we just put on it. Let this collection be C+. One can now prove, it's not a particularly difficult proof, that the resulting collection C+ of n charts is an atlas on S, and so we've recovered a smooth n-dimensional manifold from the data provided to us by S and C. Okay, so we built up a manifold from a collection of privileged coordinates. Okay, second step. We want to recover some structures on top of this manifold. Like we want to, in particular, in the form of smooth tensor fields that are laid down on top of the manifold SC+ that we've recovered from our locally G-structured space. There are a couple of equivalent ways to do this. I am going to discuss just one because it's perhaps the most intuitive of the bunch. Okay, so first, one notices that the maps in our collection C of privileged coordinates suffice to determine what we will call the coordinate transformation pseudogroup on S. Okay, so the maps in C, what's going on here is they are allowing us to drag back the pseudogroup G onto X, onto the manifold that we built on the left-hand side of the screen. So intuitively, this coordinate transformation pseudogroup, all of the maps between subsets of S, between open subsets of this manifold, that switch us from one of our privileged coordinate systems into another one. So more precisely, gamma, this coordinate transformation pseudogroup, contains maps of the form C inverse after D, where C and D are in our collection of privileged coordinates, and this composition is defined. Okay, so these, you can think of these as the coordinate transformations between our privileged coordinates in C. Okay, so now we have a pseudogroup on our manifold on the left-hand side. We can pseudogroup now to build up tensors on the left-hand side. In particular, what we do is we consider those tensor fields alpha on the smooth manifold S that are implicitly defined by gamma. So that is the smooth tensor fields on S that remain unchanged when pulled back via any of the maps in gamma. Okay? We equip S with these tensor fields. We're implicitly defining a collection of tensor fields on the left-hand side. And now, you guys, we've done it. We have a smooth manifold with some structures defined on top of it. Okay, so like question 1 answered in a particularly natural way. We've recovered from a locally G-structured space a smooth manifold with some tensor fields on it. And this captures a sense in which one can use privileged local coordinates in the framework of locally G-structured spaces to present a geometric object. Okay. So we have a recovery procedure. The idea behind it is pretty simple. I kind of mentioned it earlier, but let me just say it again. Now you've had all of this. You've heard it all once. Let me sum it up. So we have our pseudogroup G on the right-hand side affirming this pseudo, like laying down this pseudogroup T on Rn is tantamount to saying which structures on Rn we care about, right? They're the structures that are invariant under the maps in G. We use the collection of privileged coordinates in C then to pull these structures back onto the manifold on the left-hand side. Okay, so that in essence is all that's going on. Okay, so our main question, we come to our question of the day. Can every relativistic spacetime be recovered from a locally G-structured space? Okay, so I'm actually going to give two answers. My first answer is yes. My second answer is going to be no. And then I'm going to briefly comment on the relationship between the Okay, so let's start with answer one. Yes, there is a sense in which every relativistic spacetime can have all of its structures recovered from a locally G-structured space. Okay, this is going to take a little bit of work. Okay, so suppose we have a relativistic spacetime MG, like this one here. The first thing we have to consider is which locally G-structured space should we be looking to recover the structures of this spacetime? Like, what's our best bet locally G-structured space? Which one should we be looking to build back MG? Okay, I'm going to have to define this for you. We're going to call it the locally G-structured space determined by a relativistic space. The locally G-structured space determined by the relativistic spacetime MG. And then we're going to recover back from this locally G-structured space that I define these structures, okay? Okay, so an important definition. We will say that a relativistic spacetime Rn G prime is a representation of Mg if for each point P and M, there's an open set containing P and some open set O prime subset of Rn, such that when I restrict the metric G to O and restrict the metric G prime to O prime, the result is isometric spacetimes. O, G, and O prime G are isometric. Okay, so intuitively, a representation of Mg is a spacetime with underlying manifold Rn that reflects, it like captures the metric G, but chunked up differently. It reflects the structure of Mg in the following sense. Like this part of Mg is isometric to this part of Rng prime. This part of Mg is isometric to this part of Rng prime. Okay, but we're guaranteed that our underlying manifold on the right-hand side is Rn, which is going to be important because we're trying to build up a collection of privileged coordinates which are maps to Rn. Okay, so that's why we're doing the thing that we're doing here. Okay, so one can show now that every relativistic spacetime has a representation. This is non-trivial, but I can sketch my method of proof. My method of proof was I texted JB and just said, does every relativistic spacetime have a representation? He wrote back with a proof. We can talk about this if you would like. Every relativistic spacetime has a representation. Okay, so now I'm going to build up from a relativistic spacetime Mg the locally G-structured space that it determines. Now that we have this resultant and we can define up this best bet locally G-structured space, okay, for recovering the structures of our spacetime. So let Mg be a relativistic spacetime and pick some arbitrary representation of it. We know some such representation exists. Pick one. Okay, we need to define G, we need to define S, we need to define C. G will just be the isometry pseudogroup of the representation, okay? S will be the underlying point set of our manifolds M, and C will be the collection of isometries between open subsets, the spacetime on the left-hand side, and open subsets of the spacetime on the right-hand side. Okay, so quick remark. One can see now why it was important that the spacetime we chose on the right-hand side was a representation. Since it's a representation, we have a guarantee that every point in M is in the domain of one of these isometries, okay? So our privileged coordinates in C that we built cover N. Okay, so one shows that the resulting SC is in fact a locally G-structured space. And moreover, different choices of representation. So remember, we made an arbitrary choice at the start, choice of representation. Different choices of representation will result in isomorphic locally G-structured spaces. So there's a sense in which that choice didn't really matter. It was important to us that we had a representation. It's not important to us that the representation was unique because the locally G-structured space you get out is unique up to isomorphism. Okay. So we have a well-defined method of recovering a locally G-structured space up to isomorphism from an arbitrary relativistic spacetime. We will call this locally G-structured space the locally G-structured space determined by the relativistic spacetime. Okay, so remember what we're doing here. We're building up our best bet locally G-structured space for recovering the structures of MG. We've now done that. Now I want to show you a sense in which one can recover from this SC that I've built all of the structures of MG. Okay. So in particular, one proves this proposition. The proposition is essentially just saying it's capturing the really close relationship that holds between MG and the locally G-structured space that it determines. Okay, so the following two things hold. First, the manifold that you recover from SC is just the manifold M that we began with. If one employs the recovery procedure that I was sketching in answer to question 1, you apply that to SC, you get back the manifold M. Okay, that's the first important fact. Second, the coordinate transformation pseudogroup that we built on S is just the isometry pseudogroup of MG. Okay, so MG and its locally G-structured space that it determines, they're super closely related to one another, like captured in this sense. Okay, so we now have, we can actually answer this question, at least give my yes answer. Can every relativistic spacetime be recovered from a locally G-structured space? So given our method of recovery described above in answer to question 1, there is a sense in which the answer is yes. Okay, so consider the locally G-structured space determined by some spacetime MG. Our proposition from a couple slides ago implies that the manifold I recover from SC is just the manifold M. And moreover, since the metric G is implicitly defined by my coordinate transformation pseudogroup gamma, how do I know that? The coordinate transformation pseudogroup gamma is just the isometry pseudogroup of MG. So G is implicitly defined by the coordinate transformation pseudogroup gamma. So I recovered G as well via implicit definability using the coordinate transformation pseudogroup gamma. Okay, so this captures a sense in which my locally G-structured space SC recovers all the structures of MG. It recovers its manifold and it recovers its metric. Okay, so that's the yes answer. So in essence, this is what we've done here. We've given one account of what one might mean by the privileged coordinates of a spacetime MG. And we've shown that on this account, all of the structures of MG are invariant under changes of privileged coordinates. G is invariant under changes of privileged coordinates on this particular account of what the privileged coordinates of MG are. Okay. So that's the yes answer. So I'm going to give the no answer also. And the no answer is a slightly better answer. So I'm going to give the no answer and then I'm going to explain why it's better and what the mistake was in answer 1. Okay, so we begin with a couple lemmas. So first, there are non-isometric relativistic spacetimes with underlying manifold Rn that have trivial isometry pseudogroups. So that is in JB's terminology, there are non-isometric Heraclitus spacetimes with underlying manifold Rn. Okay, how does one prove this? It's super easy. one takes JB's Heraclitus spacetime that he built for us, considers two open balls in it, restricts the metric on the spacetime to those two open balls. That results in two spacetimes. These cannot be isometric, because if they were, our original spacetime wouldn't be Heraclitus. Similarly, they must themselves be Heraclitus because they're little regions of a Heraclitus spacetime. And also, since their underlying manifold is an open ball, it's diffeomorphic to Rn. Okay, good. Proof. Okay. Also easy to prove is the following. Suppose that we have two locally G-structured spaces that have trivial coordinate transformation pseudogroups. So that is coordinate transformation pseudogroups that only contain identity maps. Then if the manifolds that these two locally G-structured spaces determine are diffeomorphic, then the locally G-structured spaces themselves must have been isomorphic. Okay? So from these two lemmas, it follows that there are non-isometric relativistic spacetimes that determine isomorphic locally G-structured spaces. Okay. Can I try to give the proof orally? This isn't always successful, but I'm gonna try nonetheless. We have what it takes to do this. Okay, and the idea behind the proof is easy to appreciate. So we consider the two non-isometric Heraclitus spacetimes whose existence is guaranteed by the lemma 2 slides ago. Consider those two guys. Our earlier proposition implies that since they have trivial isometry pseudogroups, the locally G-structured spaces they determine must have trivial coordinate transformation pseudogroups, because our proposition said that those two things are the same. Similarly, the proposition also implies that the two locally G-structured spaces recover the same manifold, because the spacetimes that we started with have the same underlying manifolds. Okay, hence the lemma on the previous slide kicks in. We have two locally G-structured spaces determined by our relativistic spacetimes. They have trivial coordinate transformation pseudogroups. They determine the same manifold, so they must be isomorphic. Okay. So this captures a sense in which the answer to this question is no, but it's worth unraveling just a bit. I'm gonna make three remarks here. So why does this mean that the answer is no? Like, why does this theorem imply that this answer is no? Or like, how do we get a no answer out of this theorem? Well, what we've shown here is that the framework of locally G-structured spaces, at least on its own, lacks the expressive resources of the standard differential geometric framework. So one cannot use it to present both of the two spacetimes that appeared in the previous theorem. They look the same from the perspective of locally G-structured spaces. They determine isomorphic locally G-structured spaces. Okay, let me say this another way. Another way to say this, like the structural differences between some non-isometric spacetimes are washed out when one moves to the framework of locally G-structured spaces. Because in moving to this framework, we had spacetimes that were initially non-isometric. We moved to this framework, and the locally G-structured spaces that they determine are the same. They're isomorphic. Another way to say this, you give me this locally G-structured space. I can't tell you which of these two non-isometric Heraclitus spacetimes I was talking about. So that means this framework doesn't have the same expressive capabilities as the standard differential geometric framework had. It doesn't give us the ability to distinguish between non-isometric Heraclitus spacetimes. Okay, so that's why this means the answer is no. But what was wrong with answer one? I'm sure that a lot of you have actually seen this already. So we mentioned in answer one, the yes answer, that there's a sense in which all of the structures of MG are recoverable from the locally G-structured space that it determines. We didn't give any argument, though, that those were the only structures that were recoverable from the locally G-structured space that it determines. It may be that this locally G-structured space is such that many different metrics are implicitly defined by its coordinate transformation pseudogroup. Indeed, in cases where the relativistic spacetime has a trivial isometry pseudogroup for Heraclitus spacetimes, every metric on top of the manifold M is implicitly defined by the coordinate transformation pseudogroup because it only contains identity maps, and every metric is invariant under a collection of identity maps. So the sense in which, another way to say this, the sense in which we really recovered G on M was weak in answer to question 1. If we recovered G, we successfully recovered all other metrics on M. Okay. Last. In essence, what we're doing here is we're simply pointing out that the recovery procedure I described in answer to question 1 is not well defined if we think of it as a map from locally G-structured spaces to relativistic spacetimes. It may be that given a locally G-structured space, there's more than one metric that's definable using the structures of that locally G-structured space. So we do not recover a unique relativistic spacetime from SC. Okay. Okay, a third question. I said there were 4. Third question. Where does Sweden keep his armies? Do you know? In his sleeveys. I was once told that every good lecture contains a proof and a joke, and this is the joke. Okay, while we're here, Jamie, I told you I didn't have any good jokes, and look where it didn't help me. Look where we are now. Okay, so I do have one other relevant question that I'd like to ask. So we've seen that this method doesn't always work. This like Kleinian subtractive external method doesn't always work for presenting a relativistic spacetime. In these cases where relativistic spacetimes have very few symmetries, the method breaks down. So under what conditions does it work? Okay, we can give a kind of answer to this question. Which relativistic spacetimes can we present by giving a locally G-structured space? Okay, I'm going to give 2 definitions and kind of unravel them a little bit. So first, we will say that a relativistic spacetime MG is determined by local isometry if all relativistic spacetimes, like any other metric you could put down on G, that determines the same isometry pseudogroup. So any other metrics on G that have the same local isometry, any other metrics on M that have the same local isometries as G, are isometric to the spacetime we started with. Okay, so let me unravel this just a bit. So suppose we're dealing with some spacetime that's determined by local isometry. What this means is the following. It means that if I know the collection of symmetries of the spacetime in this precise sense, like if I know its isometry pseudogroup, I can tell you what the spacetime was up to isometry. Right, because any spacetime with that same isometry pseudogroup must be isometric to it. Yeah, okay. Not all spacetimes are like this. In particular, our Heraclitus spacetimes from earlier are not determined by local isometry. They have the same isometry pseudogroup, the trivial one with only identity maps, and they are not isometric. So not all spacetimes are determined by local isometry. Okay, a second definition. Oh, let me say one more thing on this definition. So intuitively, like, the more symmetries a spacetime admits, the better it's shot at being determined by local isometry. Heraclitus spacetimes emit like none, so the symmetries aren't telling you all that much about the structure of the spacetime. Determined by local isometry is a condition saying that the spacetime has a lot of isometry. It has a lot of symmetry. Okay, second definition. A relativistic spacetime MG, we will say, is locally presentable if for any other relativistic spacetime M prime G prime, if they determine isomorphic locally G-structured spaces, then the spacetimes themselves must be isometric. Okay, I always find this one a little harder to parse than the last definition. So let me say something that might be helpful. A spacetime that is locally presentable is one that can be genuinely recovered up to isometry from the locally G-structured space it determines. 4, suppose that MG is locally presentable. then if a relativistic spacetime determines the same locally G-structured space as MG did, then it must be isometric to MG. So from the locally G-structured space that our spacetime determines, I can recover back up to isometry the spacetime that I began with, because any other spacetime that determines the same locally G-structured space is like the same. It's isometric to the guy I started with. Another way to put this is for locally presentable spacetimes, if one knows SC, then one knows MG. You know the locally G-structured space that our spacetime determines, you know the spacetime up to isometry. Okay, so this is not super surprising given the recovery procedure that I was describing, but it's worth making explicit nonetheless. So one can prove that a relativistic spacetime is locally presentable if and only if it is determined by local isometry. Okay. So in other words, a locally G-structured space can be used, locally G-structured spaces, the framework of locally G-structured spaces can be used to present all and only those relativistic spacetimes that are determined by local isometry. Okay. So one can show that Minkowski spacetime is determined by local isometry. One can show, going back to the story that I told at the beginning, Euclidean space, the standard Euclidean metric, it's determined by local isometry. And so these can be presented using the apparatus of locally G-structured spaces. One conjectures that this is more the exception than the rule. Okay, I'd like to conclude by making a few remarks. Okay, so first, a precedent for these results in the literature. So it's been remarked before that the move to general relativity represents a move to a Riemannian conception of geometry and away from a Kleinian conception. So in the 90s, John Norton, in a series of papers, put forward ideas like this. He attributed them to Cartan. So Norton says, like, Einstein used something like Klein's strategy in the context of special relativity. It was entirely appropriate. Special relativity provided a beautiful illustration of the power of Klein's approach, but general relativity threw into physics and philosophy the antagonism that existed between the two principal directors of geometry, Riemann and Klein. The spacetimes of classical mechanics and or special relativity are of the type of Klein. Those of general relativity are of the type of Riemann. Okay. So our results here today sharpen these thoughts. Like we've kind of delivered on this promissory note. All and only those spacetimes determined by local isometry, of which Minkowski spacetime setting of special relativity, setting for special relativity, is one, are presentable in a Kleinian framework, at least if what we mean by Kleinian framework is framework of locally G-structured spaces. Okay, but we can do a little bit better than this. So we can kind of clearly see why this Kleinian approach doesn't work in general relativity. Okay, it is not the additional flexibility one has in GR to formulate a spacetime over an arbitrary manifold rather than R4. So the Heraclitus spacetimes that we are using to generate our first theorem have underlying manifold R2. It's not the manifold weirdness that you get moving from special relativity to general relativity. Rather, it's the metric flexibility that you have. So arbitrary metrics are not presentable using this Kleinian apparatus. They're way too flexible. Some admit too few symmetries. The Minkowski metric admits a ton of symmetries. General relativity metrics do not admit this many symmetries. Along a similar line, one might have thought that the Kleinian program fails when one only considers global symmetries of the spacetime, but that its prospects are better when you also take into account local symmetries. This is not the case, though. That's what we've shown here. This local Kleinian program, even as represented by the framework of locally G-structured spaces, even when you take into account all of the symmetries between small regions of your space-time, that doesn't always give you enough information to fully capture the structure of the space-time you started with. So even this like Klein program on steroids doesn't work. So it's not a global versus local thing. Okay, so I'd like to conclude by mentioning a few possible routes forward for a proponent of locally G-structured spaces. And more, this is just an opportunity for me to suggest other things I want to think about and what I think future work here should look like. Okay, so first way one might go. One might try to formulate a better recovery procedure. So we showed here that one particularly natural way to recover relativistic spacetime from a locally G-structured space does not work. And as I mentioned before, the problem was just this recovery procedure was not well defined. This is, to my mind, the most natural recovery procedure. It does, like, it's not like a junky procedure. We got a yes answer out of it. Nonetheless, one might argue that there's some kind of better recovery procedure. So for example, one might notice that the problem here at bottom has to do with implicit definability. This property of being invariant under a collection of maps is known to be a particularly weak kind of definability. So one might pivot and try instead to recover a metric using some variety of explicit definability. Change our recovery procedure. Okay. So two points on this. First, note that this would require a kind of change in spirit, as so far what folks have been talking about is structures invariant under changes of coordinates, which to my mind suggests a kind of implicit definability. Invariant under changes of coordinates. That reads to me like implicit definability. The main roadblock here is that it's really hard to talk about explicit definability when one is not working within the confines of a formal language. There are people here who are thinking about this kind of stuff. Okay, another route. One might argue that locally G-structured spaces work in some interesting restricted context. So we have shown that they work just in the cases where relativistic spacetime is determined by local isometry. So one might investigate this notion of determined by local isometry. I think that we should do this regardless. But after investigating this notion, one might somehow argue that all physically reasonable spacetimes are determined by local isometry, or that all spacetimes are in some sense sufficiently close to some spacetime that's determined by local isometry, something like this. I have to confess I'm not super optimistic about this route. But it's definitely something that we should think about, in particular investigating this notion, seeing which kinds of spacetimes are or not determined by local isometry is a worthwhile thing to do. So alternatively, another flavor of route 2, one might argue that locally G-structured spaces can be used to capture the content of some entire other interesting physical theories. So the symplectic manifolds of Hamiltonian mechanics, or flat classical spacetimes, a setting for standard Newtonian gravitation, for example. I'm actually very optimistic about this route. Okay, lastly, another kind of way forward. One might argue that locally G-structured spaces, while they don't tell us everything about the structure of relativistic spacetime, they still tell us something about it. Like, try to make precise what it is they're telling us. They don't allow us to recover the exact metric up to isometry, but they're telling us something interesting about relativistic spacetimes. Okay, so one possibility, this is suggested at some places by Jill North, is that a locally G-structured space captures the amount of structure that the spacetime has. Privileged coordinates determine amounts of structure. They might not tell us exactly, the structure up to isometry. They tell us how much structure the object has. This is worth investigating, but my spidey senses are tingling, you guys. I think that exactly the same kind of argument that we were putting forward in the first half is going to work here. Like, I'm not optimistic that this is going to work. Okay, another possibility, as David mentions in his paper on this stuff, every relativistic spacetime is such that the underlying manifolds can be presented using a locally G-structured space. A manifold is just a locally G-structured space for a particular choice of G, namely let G be the collection of diffeomorphisms between open subsets of Rn, let C be your atlas on the manifold. That is a locally G-structured space. Okay, so certainly part of the structure of MG can be presented using this apparatus. It's manifold structure. This is definitely true. Let me make two small points on this, neither of which I consider to be in tension with anything that David said. So first, does this give rise to a Kleinian presentation of general relativity? I mean, look, not fully, right? Because we're only presenting the manifold. We're not presenting the metric. One might nonetheless be tempted to say that we can take a kind of hybrid Klein-Riemann approach, present the underlying manifold using the Kleinian apparatus of locally G-structured spaces, then transition to, the full apparatus of Riemannian geometry to find the metric in the normal way. Our results here imply that in order to characterize G, you have to take a different approach than pure Kleinian to present the metric. This hybrid approach, though, is not all that hybrid. That's the thing. At least it is at heart no different from the standard differential geometric presentation of MG. Because a smooth manifold in the standard presentation is just a locally G-structured space. So we haven't done anything different if we're taking this hybrid approach. So, I mean, 100%, this approach represents legitimate and informative way to formulate GR, but one that's no different from the normal way of formulating the theory. Okay, so second, modesty is a good thing, but going this route, at least for some purposes, will be too much of a good thing. Okay, for some purposes. If one just wishes to point out that there's an echo of these Kleinian methods like lurking below the surface in general relativity, then that's fine, that seems true. In defining a manifold, one employs kind of these methods. But claiming that the manifold structure of MG can be presented by appeal to privileged coordinates in the framework of locally G-structured spaces does not suffice to substantiate some of the bolder claims about coordinates and structure that have been made. So for example, North writes that the coordinate independent invariant features correspond to the intrinsic nature, the genuine structure of the space. If one includes as privileged coordinates the entire atlas of M, as this route is suggesting we do, then the metric doesn't count as part of the intrinsic nature, the genuine structure of space-time, because coordinate transformations are not guaranteed to be isometries because we've included too many maps in our collection of privileged coordinates. The coordinate transformations are just guaranteed to be diffeomorphisms. So in sum, this route is too modest, at least for proponents of the idea that privileged coordinates determine structure. Okay, that's all I have. Thank you.
Well, I'm pleased to see that I have had an influence on Thomas and JB in at least one way, which is that they have both taken up all of their allotted time.
I think we have time for 2 or 3 questions.
You started me late. Small talk over there.
David, Neil.
Thanks, that was a lovely presentation. An observation, there's a shift that happens across the course, which I think is legit, but worth noticing.
Yeah.
Initially, we're talking, as I was talking, about how one characterizes theories in coordinate ways. But the sort of bulk of what you're talking about and what Kerry was talking about how to characterize specific spacetimes in coordinate ways. Now, in pre-gravitational physics, that's innocuous because it's one model, exactly. But of course, that's not true in GR and true in Newton either. And so their particular space-time is a specific solution to the mathematical equation.
Yeah.
And I wouldn't have expected, even prima facie, that these kind of Kleinian methods had any chance of characterizing specific solutions to the equations, any more than I'd expect these methods to characterize specific solutions to the Klein-Gordon equation of flat space-time. They can characterize the general structure of the Klein-Gordon theory, but not specific solutions to it. And it feels like something similar is going on here. I mean, if one takes the Einstein field equations, presents them in coordinate form, looks what geometry that implies, what does one find? One's going to find they imply differential geometry and a rank 2 tensor as a dynamical entity, involving under that on that geometry. But it further happens that that's rank 2 tensor in a different sense of geometry has a geometric interpretation, but that doesn't seem in tension with the idea that the Kleinian methods are characterizing the geometry of theory as distinct from the geometry of specific solutions. And then that seems sort of similarly true to some extent to what North is saying about structure. I mean, so it certainly seems to follow from North's framework that the metric is not intrinsic structure, the metrical structure is not intrinsic structure in space-time. I don't know what North thinks about that, but at least something like Rebelli is going to be pretty relaxed about that. Saying, no, that's fine. The intrinsics, the metric is just more matter. It's doing dynamical stuff.
Yeah, so I suppose I would have thought prima facie that it's a little bit weird, or it's at least worth pointing out that if one is taking this approach, one is then committing oneself to the idea that the metric isn't part of the intrinsic nature of space-time. That is a bit strange, though, don't you think?
Well, and I think a very basic divide here is going to be between people who think that the metrical goings on in GR are somehow special, and people are going to think that GR is just one more very interesting dynamical theory. I think the sort of way I'm sketching it is much more compatible with that latter framework. Rebelli is going to be much keener on that latter framework. There are perfectly good cases for the reverse case, but if you want to say there's nothing more special about the fact that generic metrics are not characterized in this way than the generic scalar field solutions to the Pythagorean equation are characterized in this way.
Yeah. Okay, so I totally agree. Like, whether or not the Kleinian apparatus works is for a particular theory is sensitive to the question of exactly how we're conceiving of the models of that theory. Yeah, I totally agree. Like Hamiltonian mechanics, take that for example. I believe that you can do it using locally G-structured spaces to characterize a symplectic manifold. I don't know how you would do it if you add in the Hamiltonian, for example.
Yes.
And so, this is maybe one way to understand what you're saying. You're saying, is the metric G more like the symplectic form, the general relativistic metric G more like the symplectic form, or do we want to think of it more like the Hamiltonian?
I'd say even more, I think about it as the phase space point.
Yeah.
If the G's correspond to different solutions to the field equation.
Yeah, thanks.
Yeah.
Just on that, I mean, one particular way that you might think about decomposing, I mean, particularly if you start decomposing the metrics, for example, the tetrad formalism, and there's like some grounds for thinking that then metric kind of breaks down into a kind of, I don't know, generic part, which is like it's Minkowskian nature, and then, but the dynamic, and then the connection would look more like the thing that makes a metric special. It might be that like the former of those admits a characterization by something like these sorts of methods, but the latter part doesn't potentially.
Yeah, so let me say again the thing that I showed, because this is getting too fancy above my pay grade, but I can say the thing that I did. So, look, all we showed is that if you're thinking of general relativity, models of general relativity as manifolds with Lorentzian metric, you can't present those using Kleinian apparatus. Now, you might say that's not the thing I was trying to present in the first place. Fine. That's the question that I was interested in, whether you can present relativistic spacetimes using this other framework. Yeah.
So that wasn't actually my question, but I'm aware we're.
Mm.
Can I ask that question anyway?
Well,
No,
the
no,
caterers are standing outside to take this away.
Yeah, so that, never mind.
But there is going to be a sort of open discussion period at the end of the day. So maybe write it down and we'll come back. Thank you, Thomas.
Imagine.